Hey there, Alga Talkers! Welcome to another episode of the AlgaTalk Podcast. On this episode, I talked with Dr. Lauren Biermann, who is a marine remote sensing scientist with a background in molecular biology, oceanography, biogeochemistry, and optics. In 2018, she joined the Plymouth Marine Laboratory, where I met her for this AlgaTalk. Her research is primarily focused on the detection of floating plastic debris in rivers and coastal waters, using high-resolution imagery collected by satellites in space. But we discuss how these satellites can detect algae, from toxic algal blooms to seaweed farms offshore in China. She leads the EUMETSAT ocean training contract, teaching graduate students and early career scientists the skills to independently access and apply remotely sensed data across the Copernicus Marine Data Stream Service. EUMETSAT is the European Organization for the Exploitation of Meteorological Satellites, which is responsible for the launch and operation of the European systems of meteorological satellites, and for delivering the satellite data to end users, as well as contributing to the operational monitoring of climate and the detection of global climate changes. She also contributes to a number of Plymouth Marine Laboratories research projects, where she works with an excellent team of programmers to integrate machine learning techniques. This is where we met for our AlgaTalk, when I attended the British Phycological Society's annual conference in Plymouth back in 2020, before the COVID. Without further ado, here is Dr. Lauren Biermann and observing algae from space.
I'm Dr. Lauren Biermann, and I work for Plymouth Marine Laboratories as a remote sensing scientist. And what that really means is that I get to use data from satellites. And there's a whole bunch of stuff I can do from satellites, but I think the things you're most interested in are when I look at algae, exactly.
Entirely.
And there's two satellites that I use to do that, Sentinel-2 and Sentinel-3. And Sentinel-2 is a European Space Agency operated satellite, and Sentinel-3 is a EUMETSAT operated satellite, but they both fall under the Copernicus program.
Can you tell me a little bit about the EUMETSAT program, how it got started, how it kind of folds into now what you're doing with it? Kind of just a little brief background of what the European Space Agency is doing and how it came about that these satellites exist and being able to be utilized.
Sure. Well, I mean, everyone knows about NASA, right?
Right.
NASA's an American sort of led space program, and it goes and collects data from satellites, and it's freely available to the world. Well, the European Space Agency is exactly the same, and so is EUMETSAT, but they fall under the Copernicus program, which is a dedicated sort of European, but also sort of global program that has said we need data collected for environmental and industrial purposes.
Right.
So data are collected by satellites and then made freely available to the world. And
these satellites are European launch satellites.
Correct. So these are European satellites. So we've sort of taken the American program and progressed it. We have slightly different requirements. The American program is really focused on getting data on a daily basis. We tend to get data at high resolution, and then we have two satellites working in tandem to try and get as much data as possible, but only Sentinel-3 collects data on a daily basis. The other ones collect higher resolution data, and you'll get an image sort of every few days.
So you try to use both these satellites to complement each other.
Exactly, because the main problem when you're looking at data collected by satellites, the optical data with which you can see plants, is that they can't see through cloud.
Right.
And the world's a really cloudy place.
Yep.
So the more satellite sensors that you have up there, the better chance that you have of finding patches between the clouds, right?
Right.
And there are different ways that people get around cloud. You can merge things together and try and patch the cloud sort of gaps with data. But one of the best ways to do it really is to double your chances and to have more satellites out there to collect the data.
Great. And of course, you're not even looking through clouds, you're also looking through the oceans or the surface. You are trying to get even deeper. How deep can you actually look into the ocean? Is it just the surface? Or how many layers can you actually go down to see? Because seaweeds grow and algae grows at different levels.
Depths, exactly. So that is one of the limitations of satellite remote sensing, in that a lot of the time you can only see to an optical depth. So Sentinel-3, for example, has a sensor aboard called AlgaTalk, which is an ocean color sensor, and it can see to a depth called 1 optical depth, and that varies depending on how much is in the water. So obviously, if you have really turbid water or water that's got a lot of algae in it, even with your human eyes, you're not going to be able to see to the bottom, right?
Yeah, absolutely.
And the satellite has the same sort of challenges. So it will see to an optical depth. Sometimes that can just be the very surface, and sometimes that can be like 10 meters. But it really just depends on how clear or how mucky your water is. It's the same thing. If you're looking at a lake and you know that on a very clear day with very clear waters you can see the stones at the bottom, great. But like in the summer bloom where there's loads of green stuff in the water, you're not going to see the stones. It's the same sort of thing for satellites.
Right. But actually, I mean, it might be good. I mean, for certain algae, because they kind of bloom and because you see such a mass and you can't go any deeper, you kind of know, all right, that's definitely a bloom that is growing, and you can identify it easier.
Exactly. So that's it. We know we use the model of what very clear water looks like, and then we say anything that deviates it has got stuff in it.
Right.
Now, what is the stuff? Is it green stuff or is it like silt? And so if it's green stuff, then it's plant material, then it's algae, and that's the stuff that we're looking for a lot of the time.
Entirely.
Yeah.
2 satellites, kind of like there's macro and micro algae.
Yeah.
Does either one have more of, is better for looking for micro and macro, and which one and why?
Well, exactly right. So Sentinel-3 is the satellite that's run by EUMETSAT, and it's a marine dedicated satellite. It's called the Blue Marble satellite because it's dedicated to the oceans. And that's the one that looks for phytoplankton, so your microalgae. And it's able to collect data at 300-meter resolution every single day all over the world. So you get a global composite of chlorophyll A in the water everywhere in the world. As long as it's not too cloudy, then that means whatever region you're interested in, you can get a daily update. And that's amazing because obviously if you want to see changes that are seasonal or weekly or regional or local, having a daily image every day is really important because some of these phytoplankton patterns are really transient, and you want to capture those. Other ones out in the middle of the ocean can persist, for example, in an eddy for months. And so,
and stick around one area, like the sargassum belt is kind of always there. But of course, algae, like most plants, like all plants, are seasonal. So you want to be able to follow that over the time and understand, is summer more, is the winter have more? Where exactly is the best place to actually follow it? And I'm guessing also the southern and northern hemisphere also there's a bit of a difference.
Oh, absolutely. And what's interesting is sometimes you'll find that a lot of the time we think of plants blooming in the spring, but sometimes the most interesting bloom happens outside of the spring-summer understanding. Sometimes you'll get a winter bloom. For whatever reason, there's nutrients that are recharged into the water. Storminess will stir things up and suddenly you have an opportunity for phytoplankton to bloom again. So you don't want to say, well, I'm biased towards the spring and summer bloom, that's what I'm interested in. Some of the time those phytoplankton will go below an optical depth that satellites can see to because they're light stressed.
Right.
So you want to just have a continuum all of the time. You want to be looking, depending on what you're looking for.
Right, because like you were saying, phytoplankton is transient, but it reminds me of, like, let's say you're trying to follow whales. They're going to be maybe in one spot, and then months later they're going to be in another.
Exactly.
And it allows you to be able to follow them a lot better.
Absolutely.
How new is this? Is this like a kind of a new program?
Yeah, so the Copernicus program has been running for a few years in terms of the fact that the satellites have been up since about 2015. So that's not a lot of data if you're trying to understand things that are being driven by climatological changes. But we have been able to combine some of the data with data that's been collected previously by NASA satellites. So MERIS is a satellite that NASA launched. It collected data for quite a while, I think up to 10 years, just over. Also at 300-meter resolution, similar bands to Sentinel-3. So we've been able to try and stitch things together so that we can create a longer time series, because time series has become really, really important if you're trying to
understand climate change.
Trends. Exactly.
And prove to people that some people still don't believe that climate change actually is happening.
That's it, and we
they
really
want the data, and you're giving it to them.
Exactly, and we really also want to understand what's happening to the food webs, because obviously
Absolutely.
algae are the base of the marine
Right.
food web.
Totally.
Phytoplankton are in every single ocean for a reason, and they support all of these complex food chains. So
Yeah, it very much reminds you that like the canary in the coal mine,
Yeah.
algae is kind of like, we're seeing a lot of problems with the acidification,
Absolutely.
certain algae growing
Deoxygenation.
more than others,
Yeah.
taking over territory of other algae.
exactly, but also the timing of the bloom can shift by a month or a few weeks. But if you have juvenile something in the water, juvenile fish that are looking for that bloom that should be right now,
Interesting.
and there's a mismatch of time that can be 2 weeks, that's enough to wipe out a
Right.
cohort.
And you can actually see that. You can see that the fish are coming to a place that maybe months or years before you saw that there were algae blooms, and they're coming there and there's nothing there.
Exactly.
And, you know, like you say, they can be wiped out, and
Yeah.
it's
Exactly.
important to...
Any perturbation to the base of the marine food web is going to have implications further up, right? And we don't know what they are, and it's really important to know what those perturbations are. And the best way to do that is to say, well, we know what it looked like 10 years ago,
Right.
and we know what it looks like now. And is that a trend that's happened over 10 years, or is it just this year? Was this an anomalous year? It's really useful to have long time series, to have daily data in order to pick up those sorts of things.
And the Copernicus program with the 2 satellites, I'm guessing, are more advanced than the NASA ones that were sent up before.
Well, this is it. So technology advances so quickly, right? We
Right.
think about a camera that we can buy today
Yes.
versus a camera that we could buy 10 years ago. And now we're talking about putting them in space. And this
Yep.
is essentially what it is. It's this highly sophisticated camera that has multispectral bands. So most of our DSLRs have got red, green, and blue bands, and maybe into the near infrared. These guys have got 12 bands.
Wow.
So we're talking about stuff that was put into space. You know, the Landsat satellites were put into space in 1979
Wow.
for the first time.
Yeah, technology has
Okay.
changed a little bit since
It really
then.
has. So it's not like NASA's fallen behind. It's just that by the time the Copernicus program started putting instruments in space, the technology had changed a lot. And so I have no doubt that NASA, so for example, NASA are going to be putting LiDAR into space now in order to look at deep scattering layers, the stuff that are below optical depth,
Right.
which is really sophisticated stuff. That's like a laser in space.
Yeah.
And so it's just that we're supporting one another now, because it shouldn't just be up to the states to have sensors in space.
Yeah, no, it is exciting that how space research has actually advanced since even the 80s. There was still the Soviet Union and 2 separate.
Yeah.
And now with the space station, for instance, everybody kind of tries to come together.
Absolutely.
And it's very important, kind of like the algae industry and research and academia need to come together sort of the same way that the space agencies are trying to work together.
Well, that's it. And what I really like about EUMETSAT, for example, is they've put out these 2 satellites, Sentinel-3A and B, as I said, to try and get the most chance of getting a cloud-free image. And they've recognized that actually not everyone is born with the expertise to process satellite data.
Right.
So they run training programs, and they say, we will accept everyone. So early career scientists, master students, PhD students, guys who work in fisheries, that say, including this sort of data in my work would be highly beneficial. And then they run these training programs, all expenses paid, in order to train people to become experts themselves, to be able to independently do this sort of work.
Fantastic.
A lot of the time you'll go, I know this data exists, or I've heard it exists, I've seen a program on it, or I've seen a tweet about it. But how does one begin to even connect with that sort of data? It's overwhelming. It can be a bit intimidating. And what I really like about the Copernicus program and EUMETSAT in particular is how much time and effort they've put into going, we can help you.
Sorry.
So it's that sort of thing. It's not just like we've done a thing. If we build it, they will come. They've gone, actually, we'll build bridges
Right,
so that
yeah,
you can
bring
become
them
an
to-
expert.
yeah,
Exactly.
exactly. So can you tell me some of the data points that you're gathering with these satellites? What, like temperature, pH levels? What are the indications and points that you're able to use for research?
pH and salinity are quite challenging ones, but ones that we're very confident about are chlorophyll A, sea surface temperature, sea surface height, So that gets a measure of like mean wave height, wave direction, and also obviously the sea surface is changing, the height is changing. So that's a very important parameter to measure, and it also helps you track things like eddies. Obviously the sea is never flat, and being able to sort of track those sorts of things is becoming increasingly important.
How is it changing? That's actually one of the first times I've heard about.
Well, so sea levels are rising, yeah,
right?
but
Okay,
also
now it kind of makes sense.
but there's also thermal expansion of water, and there's also so warmer water is obviously more. It's bigger, if that makes sense. And so you want to be able to track things that are higher than mean sea level, even though sea level is a misnomer,
right?
Because it's different all the time.
Even during the day with the moon and
exactly, tidal as well. And so, but like some boundary currents, they're changing, and you can track that sort of thing by looking at sea surface height. So that's a parameter that we can measure with high confidence. We can use radar to look at how sort of scattering the surface of the ocean is, and with that we can look at things like boats, because they're very bright objects on an ocean surface, but also things like oil spills, because it flattens the surface of the water. So that's what we can look at from radar. LiDAR looks deeper into the ocean to look for deep scattering layers. Chlorophyll looks at algae. And then you've got true color imagery as well, where it almost mimics what you could see with your human eyes. And you can also detect things. You can go, well, that is a raft of sargassum algae that is massive, looks like an island. It's going to hit the island of Barbados, and I can see it with my own eyes. And then you can also use different band ratios to go, I can also see that it's photosynthesizing like crazy. So that's a really healthy raft of sargassum seaweed. And then you can use the same kind of logic to go, I'm going to look at an algae culture farm in China, and I can see that the quadrant that's just been hit by really turbid water is not doing very well, and we should either harvest it or write it off, because that quadrant is now, it's not photosynthesizing as actively, so we know that those plants are not doing very well. There's so much you can do for the satellite.
How are people using it right now? Like how are you doing your own research with the satellites? Yes. Or are you sharing it with other people? And they're asking you, can you look at this for me? Can you look at that? And can you give me examples of
all of the above? But I can give you some examples. So I use Sentinel-2, which is the higher resolution satellite. It's actually a terrestrial satellite, but it collects data in the coastal zone. It's very good for looking at plant health, so it's really good at measuring photosynthesis. I use it to look for two things. The first thing I look for is the possible influx of things like sargassum seaweed into European waters.
Right.
There's been a big scare in the Caribbean. We've seen this huge unexplained uptick in sargassum production, and it's been ruining beaches, and apparently there are small rock pools in the UK that have had sargassum in them. So I've been looking to see if I can spot sargassum in UK waters. But while I was looking for that, I've also started to detect floating plastics. So I can see litter mixed in with some floating plant debris. So that's some of the work that I do with Sentinel-3.
So it seems like it almost could be like a weather warning, or like a warning system.
Absolutely.
This could save people lots of money in the concept that a lot of, you're talking about, it goes to the Caribbean. People like to visit the Caribbean on vacation.
Yeah.
And these blooms are affecting the economy of these resort areas, so it would be good for them to actually know beforehand,
something's
month
coming.
Of April,
exactly. And also to see, as we said, over time, how much has that changed, where does it come from? Can we use Sentinel-3, which is that global satellite every day, to say, where is it even starting from? We know it's drifting across, but where is the production from? And the other thing is,
it's a huge amount of area to actually look at. If you were trying to do it, like, let's say the old way, which was get on a boat, put a sensor in the water, drag it across, and try to find out what's going on. It's going from the shores of Africa all the way over to the Caribbean, and that's a very large area to try to keep an eye on.
Yeah, exactly. And what's great about satellites is you have the synoptic view. You can look at every single ocean in the world on the same day. And so you can start to track these sorts of things. The other thing about sargassum, though, is it's a really interesting seaweed. The one that's proliferating, that's been in the news lately, is actually quite a rare species.
Interesting.
For some reason, the conditions over the last few years have just been perfect for this particular species, and it's gone wild, right? And the implications are not just that it ruins tourism. A lot of turtles have been found drowned in these masses because they surface to breathe. and they can't get to the surface because there's just so much sargassum in the water.
Right, and sargassum is a natural thing that does exist, like kelp forests, where fish and other animal aquatic life live under and basically in a forest.
Yeah.
But now it's too much, and obviously it's out of balance.
Exactly.
And now killing that aquatic life that's there.
Exactly, and it happens so quickly, right? From 1 year to the next, it went from this is quite a rare species of sargassum to oh my god, it's everywhere.
Yeah.
And if you don't have 10 years of satellite data or 5 years of satellite data, then you'd never be able to say, well, actually, we have never seen this before.
Right.
And we can look, we can go back in time, and we can look for it, and we can say with certainty, this is a completely rare event, and we have no idea.
And this project, the Copernicus project, would allow you to be able to maybe possibly find a solution if you kind of understand what's going on.
Exactly.
And be able to help reduce it, or, I know a lot of people are gathering it off the beaches and using it as a resource.
Well, absolutely. That's the way it should be, right? Seaweed is an incredible resource. We should be using it more.
So you could actually tell somebody, Bermuda, look out, get your
cooking pots ready.
Exactly, get your cooking
You're
pots
about
ready.
to get some really delicious seaweed that's super high in iodine and all of the nutrients you could need. For sure. And what's also really nice is you don't have to be a satellite scientist in order to use satellite data. We actually prefer collaborating with all sorts of scientists because, as you were saying, a satellite scientist is not going to know what caused a sargassum outbreak.
Right.
But if we work with seaweed specialists, if we work with people who've been doing the on-the-ground monitoring in the boats, then we can start to get a bigger picture of what's going on.
Right.
But just being able to see it from space doesn't give you any answers, which is why the Copernicus program is so great because it allows for collaboration across all sorts of disciplines.
Yeah, once again, you can tell them, take your boat over here, like you were saying with harvesting seaweed off in China, and be able to say, this, instead of, because I'm guessing these areas that they're growing seaweeds are very big areas.
They're massive.
And to take a boat and try to cover all of it is nearly impossible.
Exactly.
Or a lot of work.
Yeah.
And you're able to just go, hey, just go over in this area, pick this because this is ready to go, or it's being damaged and this is the time to harvest as soon as possible.
Exactly. And it's weird because in terrestrial context, we've been doing this for a really long time. We've been using high-resolution data to look at crop fields and to say, something's wrong in the west quadrant of that field. You're going to need to water there, or maybe you need to put someone in a pair of boots and go and take a look because something's not right. And so actually, we're catching up with terrestrial applications.
All right, yeah. Is that a coffee machine? It's got to be it's a steamer. It's a cappuccino. All right. So just to let you know, I just wanted to go over. I'm going to wait for a minute. It's all good. Well, it's the price of trying to cover something.
I hope I haven't deviated too much. There's just so much to talk about, and I get really excited because, as I was saying, I use a whole bunch of satellites to do a whole bunch of things, and it's like, how do you pin it down and talk about it neatly when I could talk about this for days.
Sure. I'm sure that all the data points, like you're saying, on a daily basis, it might be difficult for you. I'm guessing you have a whole staff that is looking at this because I don't think one person could look at all these data points and be able to follow everything because you're looking at an entire planet.
For sure, and that's what's really nice about working at Plymouth Marine Labs is we have an Earth observation dedicated group. So we've got about 40 scientists, and we're constantly just working together as like a hive of activity. And there is no problem with me literally just walking down the corridor, bashing down someone's door and going, I've just found this thing, it's really weird, have you seen it before? And we can collaborate about it, we can talk about it, and that's how I found plastic.
Wow.
I was looking for algae.
Yeah.
And I was like, this doesn't look like algae, it's weird. And I went and bashed down someone's door and I was like, look at this thing that I found, what have I found? And they were like, that's definitely not plant material. And that started off a whole sort of field of study.
Of understanding what plastics in the ocean, the famous floating island in the Pacific.
Yeah, I mean, the fact that we can see it from space is both incredibly scary and also very technically interesting because we never thought that we could.
Right. No, it sounds very interesting. Like the way that you were saying what you were bashing down the door, it seems like the beginning of a movie. Like you're running down the hallway. There's a meteor coming. There's plastic.
Oh my God!
I got these data points.
Yeah, exactly. Yeah. That's pretty much how I am at work. I'm a bit dramatic, but I'm very excited about data.
Yeah,
Yeah.
How you got tons of data now, yeah.
Yeah, absolutely.
And so if somebody...
Petabytes of data.
How much?
Petabytes of data.
Which would be?
It's like tens of terabytes.
Wow.
Yeah, we have
Okay.
a whole floor of server room.
Wow.
Yes.
Yeah, entirely.
We
For
work
satellites,
with huge
yeah.
amounts of data.
Wow.
Yeah.
And that server area and the research that you're connected with the satellites is here in
Yes,
Plymouth?
it's in Plymouth. So
Wow.
Plymouth is actually really good for marine science. We've got the MBA, the Marine Biological Institute, which is a really old, beautiful institution. We've got Plymouth Marine Laboratories, and then of course we've got Plymouth University.
Do you have the same view like they do, or?
No, unfortunately not. And their building is really old and beautiful. Ours is a bit more modern though. It's
Right.
easier to heat, which I appreciate coming from
Sure.
South Africa.
And environmental reasons
exactly.
is very important.
It's a more modern building. But we do have a view as long as you're on the top floor.
Okay.
But we collaborate across institutes, and of course all really strong in marine stuff. The Marine Biological Institute does their own algal research, Plymouth Marine Laboratory does ours, and then of course the university does their own, and we collaborate across when it's needed. And it's really great to know that you can, instead of bashing down someone's door, you can just
Right.
walk across walk across the bay and politely knock on someone's door and ask for some assistance.
Yeah, but
So
I don't think a movie doesn't start out
It
that way.
doesn't,
The
you're
guy
right.
with
It's
the information
way better with
doesn't
me,
knock
yeah.
gently on the door. He's
Yeah.
got to kick down that door and tell somebody.
exactly.
So you guys are collaborating well here in Plymouth. Around the world, if people want to know about your research and be involved or gather data for themselves from the data that you guys are doing, how do they go about
absolutely.
doing that? Have they done that?
Oh, sure. So, I mean, I can give you an example from my own work. So, for the work that I do for EUMETSAT, we run training programs. And so, last year alone, we ran a training program in China, and we ran a training program in Zanzibar in Tanzania. And so, we collaborate very actively with colleagues in Africa and in Asia. And
Which is interesting because Africa, I think in the past 10 years, seaweed aquaculture has really grown there.
Absolutely.
And they've been talking to people in Asia and back and forth. And, we know sometimes there's famine in Africa, and seaweed cultivation could be an alternate source of protein and medicine and all types of things that you
absolutely.
could get.
And also, they're very invested in supporting artisanal fisheries and making sure that traditional local populations that live off the ocean bounty are supported. So they're very invested in making sure, for example, as I said, that when you have young fish in the water, that the chlorophyll blooms are in place at the right time.
Yeah.
So we have a lot of scientists who are studying any changes to timing of those blooms and how that might impact future fisheries.
Right.
And we also have a lot of scientists who are interested in using algae as an indicator of water quality of Lake Victoria, because it gets really, really eutrophied, and you get a lot of water plants like hyacinth that have been choking the waterways.
Right.
Is that because they've introduced fish cages, or is it something that's been happening further back? Is it just that there's more of it, or is it just that we're suddenly more aware of it? And being able to go back a decade of satellite data means that you can actually say, well, water hyacinth has been there for a really long time.
Really interesting.
And in fact, what happens if you improve land and water use practices further upstream? Does that change eutrophication? Does it ensure that your water quality remains good, or in fact improves over time? So there's a lot of really interesting work.
There's this kind of problem with aquaculture. It's better than going out and fishing the ocean and taking all the fish out and actually growing them near the shore, like you're saying. But my guess would have been that the fisheries were the actual problem, putting more nutrients into the water. But you're saying that hyacinths, over the years, you can see that they've been there, and it may not be actually fisheries that are the problem.
The fish cages have only been there for a short time, but there's been farming practices, and there's been stuff being put in the water. So, for example, sewage, like in the UK, it's shocking how much untreated sewage was being washed into the ocean and just being pumped into
Florida,
the ocean. So But since we've started improving water quality practices, we can see changes to our chlorophyll patterns because there's less stuff silted in the water. There's more light available to these plants, and we're actually seeing improvements in chlorophyll patterns.
Wow.
So just changing water quality practices often has the best impact downstream. So in a way you can say, look, fish cages do need to be regulated in Lake Victoria, but more importantly, can we address upstream processes where the water quality is going to be affected by sewage or by farming practices?
Absolutely.
And so, because you don't want that much, you don't want, in Florida,
Sure,
for
in
example,
Florida, is the sugar cane.
Exactly.
The sugar plantations are pumping lots of nutrients downstream and into the ocean and creating red tides.
I was about to say, one of the biggest red tides I've ever seen was in Florida last year.
Oh.
I mean,
That's
I
worrying.
didn't, but I didn't even need to adjust any of the bands. I looked at Sentinel-2 and 3 data, and it was just brown. The first time I looked at it, I was like, I can't see the bloom. And then I realized it's because the whole scene was brown.
Wow.
Yeah, it was the biggest red tide I've ever seen.
I think that's one of the times that you got to run down the hallway and bash on the door and say,
well, exactly.
we got a problem here.
Well, we did. We went online, and there were so many news articles, because obviously we don't live in Florida, and so we don't necessarily know if we're tapped into the right news sources. But there were loads of don't go in the water. This is really bad.
Entirely.
Don't touch the water. And it was at I think it was at a high tourist season as well. Everyone was down there for holidays. And
Florida is always a high tourist.
Oh, really?
That whole area is always full of tourists. But because red tide can be extremely toxic to people, and just it's going to be killing the fish, which are going to wash up on shore, that are also going to be toxic to humans.
Yeah, exactly.
Red tide gets into the shrimp situation.
Any
people
filter feeders.
eat,
Red tide is a really scary thing. It's when you realize phytoplankton are the base of the marine food web, and we rely on them for absolutely everything. But wow, when it turns bad, it's bad.
When it turns bad, we say we turns to the dark side.
There we go, exactly.
Yeah, we had a whole thing about algae blooms being the dark side of algae.
There we go. Yeah, red tide really is fascinating. I think you could do an entire PhD on just red tide and also the conditions that are needed for it, because red tide is also a naturally occurring event.
Right.
But you go, well, what are we doing to make it worse? Is it worse?
Yeah.
Can we go back in time and look along the Florida coastline and see if it has been this bad before? And you go, actually, this is unprecedented, but then so was the water temperature that year. It was really warm. But also we know we're putting extra nutrients into the water, so are we creating conditions which in the future will mean we will always have red tides like this? Is this the new normal? And what can we do about it so that it isn't the new normal?
Your data is very important, because to get commercial agriculture to change their practices is almost like an impossible thing. So you have to sit down with them and go, these are the data points that we have, that we know this is evidence that this is a problem, and we need to change things.
Yeah, and I mean, that's it. I think as long as you have evidence to say there are downstream impacts to what's been to your sort of influence, this is the evidence, then you have recourse and you have the ability to start that conversation. But you also have legal recourse.
Right.
Because if you are someone, for example, with an oyster farm, or with a booming tourism practice that involves scuba diving, and suddenly you can't scuba dive anymore, or all of your oysters have died because of a farmer with sort of irresponsible farming practices upstream, you have legal recourse to say, here's the bill.
You can go in front of the court and go in front of the judge, and this is, from the eye in the sky, we can see that this is what's going on.
Yeah, and pro bono before, just people have called me and they've gone, look, there was some dredging activity. My oyster farm's been wiped out. Do you have any images showing that silt moving towards my farm?
Right,
and I've gone,
which kelp dredging is a major problem that seems to be growing now, is because seaweed is kind of in demand, so now everybody just look, it's everywhere. Just grab all of it. Why not?
Exactly.
And that can really harm other industries and the environment in general.
Absolutely. And we need to be so careful about how we harvest kelp, for example, because they're such an important ecosystem. So everything we do, we need to be careful with. But I think the future of aquaculture, I hope, is algae culture. Because algae cleans up the water just really well as it is. And it also incentivizes people to have good water quality because they do better under clear water conditions.
Right, when you can show them that if you do this, it will be better, then they'll do it.
Yeah, absolutely. And I mean, I don't know about you guys, in the UK, I don't see as much of an algae influence in cosmetics or in medication. But as a kid in South Africa, my mom used to force feed us these little green tablets that were full of algae, and she was like, these are brilliant for you. And I'm sure they were. And it was, it's used quite routinely in cosmetics and in hair care. And I sort of came to the UK and I was like, where's all your algae stuff?
Yeah,
should be used more. So
yeah, but even around the world we're seeing an iodine deficiency, and that's because people are not eating their algae. They're not taking their pills the way they should.
Yeah, we should be eating more vegan sushi and getting that wakame in our diet.
Absolutely.
Yeah.
Yeah. What's the future for the Copernicus program? Are there going to be more satellites?
Yeah, absolutely. So the Copernicus program, I believe, is funded until 2050. There's going to be new satellites. There's going to be, we're going to make sure that Sentinel 1, 2, 3, 5, and 6 are continued so that we can have that really long time series that we need.
Wow. So now it won't be just two helping each other. It's going to be almost a little unit of
a fleet.
A fleet. Yeah, there
what do they call it?
It's like Star Trek.
Exactly.
It's AlgaTalk.
Yeah. And the satellites are just collecting such important data, and it's really wonderful that we can look at our Earth at such high resolution. When I was doing my PhD, I was content with 1 to 4 kilometer resolution data.
Wow.
And knowing that I have a daily image at 300 meter resolution is incredible. I had a friend email me from a ship in the middle of the Bay of Bengal, and he said, we're seeing some crazy things. What can you see? Because we're on the ocean. We're collecting these point measurements, but it looks wild. Like, I don't trust what we're seeing. Can you take a quick look at where we are from satellite and tell me what you see? And I was like, oh my God, there's the most incredible front. And on one side, it's just chock full of chlorophyll A. And on the other side, it's not. So what you're seeing, because you're right on the front, is you're not imagining it. When you're collecting data in the morning, you're in the chlorophyll patch. And then you moved out of it in the afternoon.
Wow.
And you couldn't see the front, but I can.
Wow.
And it was amazing. So
it's almost like they're like contacting God. It's like, God, can you help me, please?
Can you take
I'm out here in the middle of the ocean.
Exactly, yeah.
Yeah, fantastic.
It's really incredible to be able to help colleagues like that. And we do that all the time. Can you take a quick look? Of course I can. And then the ability to literally go back a day, look at what the satellites saw of the entire Earth, anywhere in the world, and go, it's looking pretty wild out there. The data you're collecting it's amazing. I can't wait to see what you got. So,
right, yeah, absolutely. Because you still need people on the ground collecting it and being there.
Completely. And also, you know, in order to see truth, the satellite data, to make sure that you're really measuring what you think you're measuring, it is really important to have high quality standardized data collected by people in boats and on the ground. We wouldn't be able to trust the satellite data as much as we do without continuous measurements at sea as well. So we have a lot of stations that are collecting data and have been collecting data for like 25 years.
Wow.
So that we can be very confident.
And there is a standardization that they all use, so you guys are all on the same page.
Absolutely. There's a whole team dedicated to making sure that satellite data are checked with in-situ data and that we can trust it.
So a lot of people here at the British Phycological Society do have a good career. And,
absolutely.
We're going to need a lot more people out on boats and looking at satellites. And
as you said, there's stuff that satellites just can't see. You know, I think satellite data is amazing, but one of the things is it's important to love something knowing its faults as well.
Right.
And really you can't use Sentinel-2 to look for submerged kelp beds unless the water is incredibly clear. And even then, it's limited by what it can see. So unless it's on the surface, it's going to be really hard to see.
And now with this new satellite that NASA's going to put up that allows you to have more depth, they're going to share their data with you?
Oh, sure. Most of the sort of Earth observation data that NASA collects is available to the public, just as the Copernicus program does as well. The deep scattering layer stuff is going to be more about looking for deep chlorophyll layers and scattering layers that are quite well below the surface because it can penetrate to the ocean to quite a depth.
Kelp goes down many meters.
Yeah, I mean, I hadn't thought of that before, but it is a very good way of saying, there's something growing here that isn't the surface.
Right.
You know, kelp.
Yeah.
It's the first time I've thought of it, but yes, absolutely, that can be used.
Japan.
It's probably not going to be able to measure the photosynthetic activity, but you'll at least know that it's there.
And if somebody wants to be able to visit this data that you have under the Copernicus project, where do they go, and how do they find you? And
Well, so the European Space Agency makes the data available on their own portal, and it's the data hub, and you can literally just Google ESA Open Data Hub, and it will take you to the hub where you can look at the data. Sentinel-3 data is available through EUMETSAT. It's a very similar looking hub, but it's called CODA, and that's where you can get the Sentinel-3 data. The best way, honestly, is to contact me and to say, I want to know how to use this data for my project. I think it's going to make it so much more valuable if I can incorporate satellite data, and we can teach you through the EUMETSAT training program. We don't mind if you've never coded before in your life. We will teach you how to code in Python, and we will give you all of the code you could ever need to access and process satellite data. And because the Copernicus program has been really smart in the way it has organized its satellites, whatever you learn from Sentinel-3, which is your chlorophyll and sea surface temperature collecting satellite, is directly applicable to the Sentinel-2 data because the data are organized in the same way. So they're NetCDF format, and you can use one sort of process to work with all these different data sets.
Wow.
Yeah,
and
it's
then there's
really
more to come also. So
absolutely. There's atmospheric stuff for Sentinel-5, so we're looking at absolutely everything that we can see from space about the world.
Fantastic. If someone wanted to contact you, what's your email?
Yeah, so
Twitter
they can just
handle?
I'm most active on Twitter, to be honest. I like Twitter because I'll be standing in a queue and I'll check Twitter and I'll see that I've got some DMs and I'll respond to them because I have that time.
Right.
So please get hold of me on Twitter. I'm Lauren Biermann. Not very interesting, I'm afraid. I don't have a very interesting handle.
It's actually sometimes the easier way to get a hold of somebody. But
or just get hold of me at Plymouth Marine Laboratories. So my email address is lbi@pml.ac.uk, and I'd be very interested to hear from anyone that has questions about satellite data.
Fantastic. Well, thank you very much,
It
Lauren.
was really nice to meet you. Thank you.
It was a good conversation. Good algae talking, yeah.
Well, that was a different perspective on algae, this time from space. Imagine if seaweed farmers in the Philippines, for instance, were able to just click on their computers and get a God's eye view of their seaweed farm and how their farm is affecting the larger environment around them. It seems that with the help of scientists like Dr. Lauren Biermann, this may be a possible tool for algae farmers to use to be more eco-friendly in the future. And talking about being eco-friendly and environmentally conscious, I have an update for this podcast from 2020. Recently, about a few weeks ago, a student of Lauren named Luis Schreyers, I'm going to spell it Schreyers, who I am sure will be a rising star in phycology, published a research paper on green tides. So what are green tides? Well, like Dr. Biermann said, they are wild. Like their cousin the red tide, which is now causing havoc on Florida. In Brittany, France, just like Florida, when human waste from farms and cities runs into the ocean, the excessive nitrogen input feeds the ulva seaweed that blooms to huge proportions. Brittany is considered the worst affected region in France in terms of intensity and frequency, with green tides from the genus Ulva occurring every year. Using the European meteorological satellites, they monitored important interannual and seasonal fluctuations of the green tides. In terms of trends over time, green tide events did not show a decrease in extent at 3 out of 4 studied sites. The observed decrease in nitrogen concentrations for the rivers the study cites has not resulted in a reduction of green tide extents. As we can see, this new tool of using satellites could really help in monitoring and fighting global algae blooms and a host of other climate change problems. I am sure everyone in this audience wishes the scientists at the Plymouth Marine Laboratory and EUMETSAT the best of luck, and we're cheering them on. This kind of technology could also help revolutionize how aquaculture is regulated in the future. Until then, Dr. Lauren Biermann and her students will keep viewing algae and our planet from space. And until our next episode, if you keep listening, we'll keep alga talking.